one thing I want to show that is that if G is non-discrete, then of course by this fact you don't have a unit, but you can actually have something similar to a unit. Okay, that's quite useful in many cases. So here's the definition. So I want to say what is an approximate unit. So an approximate unit, let's say in the Banach algebra. Okay, so in this case, the L1 of G. Let's say the Banach algebra, let's give it a name A, is essentially a net, okay, let's say U alpha, so that what happens is that your U alpha, if you want to multiply any F on the left or on the right, okay, so you always will get a net that converge to your original function, okay. So of course, if your Banach algebra is unitable, you just pick the net to be the unit, okay? So it's actually always equal to that. But in general, you may not have a unit, but in many cases, you do have an approximate unit, or sometimes called the approximate identity. Okay, let me just say sometimes also called approximate identity. All right, so here's the theorem I want to prove. The main theorem to say is that the L1 of G actually always have an approximate identity. Okay, so has an approximate identity or approximate unit. Okay, actually to show that, we need to prove a little lemma, which is also fairly useful. It's the following. So if I have a L1 function, say f, inside the L1 of G, well, then if I consider the left shift of this f, okay, and I consider their difference, we actually prove that their one norm are going to converge to zero. We prove that their infinity norm is going to converge to zero. So essentially, left and right translation are uniform continuous. But now I want to actually show that their one norm is also converging to zero. So this is as y goes to the identity. This is going to be equal to zero, and you do the same for the right translation as well. Okay. All right. So let's first of all let's prove. So to prove this fact, first of all is because the compactly supported functions are dense in the L1 of G. So let's just take without loss of generality, f is inside some compactly supported function. So the support of f is going to be compact. Okay, so let's say it's a compact. And let's just say for every epsilon greater than or equal to 0. So first of all, let's find, because the left translation we know is uniform continuous, so we can find some neighborhood where the left translation of f, their difference, the uniform norm is less than epsilon. Okay, so let's do the following. So let's pick an open neighborhood. Let's say E inside V, there's some compact neighborhood, so that whenever y is inside V, then I have the left translation of y minus the f, their infinity norm is less than epsilon. Okay, this we know will always happen. We can assume this V to be something nicer because we can always take a symmetric neighborhood, for example, and so on. So let's assume V is equal to V inverse, okay? All right, so let's do the following. So let's let K to be everything that's basically start from the support of F, and you can left translate or right translate by V, okay? So let's do the following. So let's let K to be that. And we assume the V to be a compact neighborhood, okay? So you can always, when you multiply two compact sets, you get another thing compact, you take the union still compact, so this K is compact. All right, so because this K is compact, then let's consider what happens when you want to evaluate the left translation of F minus the F, okay? The one norm, okay? So what it is, okay, so this is equal to the following. So let's write out the definition first. So you're integrating the difference. So this is the, actually put the absolute value inside. All right, so the function you're integrating is you left translate your f by y. So you do the f of y inverse x minus the f of x. Okay, you integrate this one and you do the d mu. And this function, your f is supported on the support of f, and you do the left translation of y inverse, and you can convince yourself this one is actually supported on k, okay? But on k, each one of these is bounded above by the uniform norm of their difference. So this is bounded by the epsilon based on our choice. All right, so because of that, this is going to be less than or equals to the measure of this k multiplied by epsilon, but we know this is k is some fixed. Epsilon, as epsilon goes to 0, this whole thing will goes to 0, okay? So this one will go to 0 as y goes to the identity, okay? You can always make the measure of v to be something small enough, okay? So the mu of k is not going to be too big. As your epsilon goes to 0, this mu k won't increase, okay? All right, so this way you basically show the if you have a compactly supported function, then this is done, okay? So now if you want to say for every f inside the one function, well, then what you can do is you approximate it by a compactly supported function, let's say g, where f and g, their one norm is going to be less than epsilon, okay? So now, because G is now compactly supported, so there exists a compact neighborhood V of the identity, so that for every Y inside your V, then the left translation by this Y of G is close enough to G in the one norm, okay? So this is less than epsilon. And what you can do now is that if you want to say, let's evaluate what's the left translation of F with against f. Okay, so you do the standard kind of 3 epsilon argument. You first approximate this by the last translation of the f minus g. Okay, so basically left translation of f minus left translation of g. They're one norm, and then you do the triangle inequality. The next thing you do the ly of g minus g, the one norm, and then finally you do the one norm of g minus f. Okay. So we know the translation of g minus f, that's going to be equals to, well, less than epsilon, okay? The one norm, well, because you're integrating against the hard measure, so you do the left translation, they give you the same norm, okay? It's left invariant. So when you do the one norm of left translation, is the same as the one norm of f minus g. So this is equals to the norm of f minus g, the one norm, again, less than epsilon. And the middle one is just by your choice of the y, this is less than epsilon. So the whole thing, you do the 3 epsilon argument, you have that this is less than 3 epsilon, okay? All right, so this essentially just finished the proof of this little lemma. And now we get ready to construct a approximate identity for the L1 of G. So let's say construction of the approximate identity. All right, so what you do is the following. So let's say for every an open neighborhood U of the identity, okay, let's say open. Let's consider the following. So we can construct some function, let's say phi of u, okay? So phi of u is going to be some compactly supported function, let's say positive function, where the support of this phi of u is going to be contained in u, okay? So your space is locally compact. You can always make sure your phi of u is supported on a compact subset inside u. And then you can also make sure that the phi of u satisfy the following. It can be symmetric, okay? If it's not, then you replace it by the basically phi u plus phi u inverse. And you can also, by scaling it up and down, you can always assume that the integral of this phi u, let's say dx, or d mu x, okay, that's always going to be equal to 1, okay? You just scale it. Now we're ready to do the computation. So we want to show that the when you convolute, have on the right-hand side, if you convolute with the phi u, then that's going to be close enough to f under the one norm, okay? So let's just write down the calculation. So by definition, this is just the integral of the convolution of x minus f of x you integrate respect to dx, the left part measure, and then you expand the convolution. So this is the integral of, say, f of xy, phi u of y inverse, but we picked phi u so that phi u, y inverse, and y are the same. So let's put the y here. So this is dy, and you minus the f of x, okay? Because here we have, let me finish here first. Because here we picked this phi u of x to integrate to 1, okay, because of that, I can insert a integral of phi of y in here, okay? So I can insert a copy of integral phi of y dy so that I can group these two integral together. Okay, so this becomes the integral of, let's put the absolute value here for now. I can say, well, that's the integral respect to dy of the phi of y of the fxy minus f of x, okay? And you have the absolute value and you do dx. All right, so let's move the absolute value inside and we can do a change of integration. All right, so this whole thing is going to be bounded above by the integral of, let's do the integrate of the dx first, okay? So phi u of y is not related to that. And let's do the difference between f of xy minus f of x dx, okay? And the whole thing going to dy. And this middle thing is essentially just equals to, if you rewrite this fxy, it looks like the basically the ry of f, and then you minus f, okay, and you integrate the absolute value. So this is essentially is 1 norm, okay, so that's the 1 norm of that. So this is going to be bounded above by the integral of phi of y, and you do the this 1 norm of the right translation of f and the difference to f, okay. And because you're by the choice of the phi of y is only supported on y, so I can say this is integrate over u. So this whole thing is going to be bounded above by the supremum, okay, the sup of x inside u of the, or I say y inside u of ryf minus f to the 1 norm, okay? So this is because the phi of y is a L1 function is integrate to 1, okay? So you can show that, well, this integral, think about it as a linear functional. You multiply some L infinity function, so it's bounded above by the L infinity norm of this function, ryf minus f1 norm. We treat it as a function in y. All right, so this is bounded by the supremum, and we know the supremum is going to be equals to, well, converge to 0 as u goes to the identity, okay? So this is converging 0 as u goes to the identity, okay? As the neighborhood gets smaller and smaller, the supremum is going to be going to 0, okay? That's because of the lemma we just proved. All right, so this basically finished the proof, okay? So we now show that this if you convolute on the right-hand side by this phi u, that's going to converge to the L1 norm, okay? And they do the same thing for the left. So this finished the proof of your L1 of G, even though when it's not discrete, it never has a unit, but you always have an approximate unit or approximate identity.